Hi everybody. Today we're going to talk about how to choose between all of these different statistical inference formulas. So I posted a workshop on my website and I'm going to run through my solutions. In order to make a decision about which formula is the right one to use, you just have to answer these three questions. First, are you looking at categorical data that you can divide into successes and failures? And if so, well then you're going to work with proportions. Or do you have numerical data that you could average? And if so, you're probably going to want to say something about the average, the means. And that'll guide you into which of the different big categories of formulas are doing inference about means or inference about proportions. Once you've answered that first question, you only have four formulas, either the top four or the bottom four. And then you've got to decide, do you have one or two samples? And that's usually pretty easy to tell, although I have an example that I'll show you where you do have to watch out and be a little bit careful. And then finally, once you know if you're looking at one or two samples, then you're down to only two formulas, either the confidence interval or the t-test, z-test formula if you're going to do a hypothesis test. And to decide between those two, you got to ask, what kind of question are you trying to answer? If you're trying to answer a yes or no question, then you're going to use one of these hypothesis test formulas where you calculate either a t-value or a z-value, and then you go and find the p-value and say if it's significant or not. If you want to estimate something or answer a how much question, then you're going to want a confidence interval that'll give you a range for the value that you're trying to estimate. Okay, so those are the three questions that you have to ask, and they'll guide you to the right formula. So let's do a couple of examples. So I've posted these examples on my website, and here I've got a copy of the questions with my solutions included. So I'll just run through my solution on each of these. Let me make it a little bit bigger so it's easy to see. So the first question, I've got these two kindergarten classes, and you want to compare the two different teachers to see if maybe one's a better teacher than the other, if there's a significant difference between the two teachers. And the data is the students and whether or not they've become pre-readers, which is one of the goals in kindergarten, is you want to get kids ready to learn how to read. So in Mrs. Toodle's class, 21 kids are in the class and 17 are pre-readers. And then in Mrs. Grimm's class, only 13 out of the 19 kids have reached the pre-reader stage. So is that a significant difference? So run through the questions real quick. All right, first, what kind of data is this? Is this categorical data that you could divide into successes and failures? Yes, definitely. A pre-reader is a success. A kid who's not a pre-reader isn't ready to go on and learn how to read yet, so that would be a failure. So this is definitely a proportion situation. Next question is, do we have one or two samples? Well, there's two different classes of students, so two different groups, so two different samples. And then finally, is this a question where we're trying to answer a yes or no question? Well, it's asking, is this significant? So that's yes or no. That's definitely a hypothesis test situation. So you use the two sample hypothesis test for proportions formula, this one. I've even included the hypotheses, right? The null hypothesis is that there's no difference between the two groups, I guess between Mrs. Toodle's class and Mrs. Grimm's class. And then the alternative is actually maybe there is a difference. Maybe one of these teachers is better than the other one. Okay, moving on. Next question. A Sports Illustrated survey here where they asked athletes if they've ever received preferential treatment. Again, what kind of data is this that we're looking at? Well, getting preferential treatment isn't really quantifiable. It's just yes or no. That's two different categorical categories, right? Success category and a failure category, if you will. So yeah, this is proportions. We've got a proportion, 225 out of the total 757 athletes that were interviewed who said yes. So that's proportions, but it's only one sample, right? There's only this one group of athletes that they talk to. So we're doing proportions with one sample, and the question that we're trying to answer is a how many question. So when you're asking how many, then should you do a hypothesis test or a confidence interval? Well, a hypothesis test answers a yes or no question. A confidence interval tells you how big something is. So we definitely want a confidence interval. And so there we go. There's the one sample confidence interval for proportions formula. Cool. And then we actually do have all the numbers here. You could plug all the numbers in and get the actual confidence interval, but I didn't ask it to do that. So moving on. Next question was, if you have 16 rainwater samples from the Adirondack Mountains in New York State and you want to estimate the average pH, pH is a number, right? So neutral things are pH 7, and the lower the number, the more acidic it is. And so because it's numerical data, it would make sense to talk about the average. In fact, it flat out says estimate the average. Those are two important keywords. Because it's talking about the average, going back to my formula sheet, I don't care about the proportions formulas right now. I care about the inference about the mean formulas. And because it's saying estimate, I'm not asking a yes or no question. I'm just saying how big or how much is the average. So I want a confidence interval. And then the only other thing left is to decide is which of the two confidence intervals do I want. Do I have one or two samples? Going back to the question, notice it says 16 samples, which is a little confusing if you're thinking 1 and 2 samples, but we're using the word sample here slightly differently in this context. It's 16 individual observations that make up one group, right? So it's really just one sample with 16 observations, just phrased differently. Okay, so we're doing a one sample confidence interval because we're estimating for the mean. So this is the formula. We will have to look up the right T star. Of course, you do that by finding the degrees of freedom. Check yourself, make sure you remember how to do that. How many degrees of freedom are there with 16 observations? Yeah, it should be 15 degrees of freedom. Okay, moving on. The next example, this one is about a multi-site HIV prevention trial with a randomized comparative experiment to compare the effects of twice weekly small group AIDS discussion sessions with a single 1 hour session. So I guess the goal here is to teach people to use safe sex practices and avoid getting HIV/AIDS. And so there's two different ways you could teach people. You could do a really short 1 hour session, or you could make people attend these twice weekly small group discussions. And the question is it worth the extra effort of making these people go through this extra twice weekly program? Will it improve the outcomes? So they actually did a study about this. And the first question they ask is, we're going to use the two groups and we're going to compare the effect of the treatment and the control on each of the following variables. So in part A, the variable is whether a subject uses condoms 6 months later. So whether they're doing safe sex. Well, whether somebody does something or not, that's categorical. It's not a number, it's a yes or no. Because it's categorical, we're going to get a percentage, right? Some of the subjects will, some of the subjects won't. Success, failure, that's a proportion situation. So we're working with proportions, and all they ask us to do is to compare the effect of the treatment and the control. So there's two groups. So we're doing proportions with two groups, but it's not really clear what they mean by compare. Are they asking us to say, oh, there's a difference? Well, if so, then all they really want is a hypothesis test. Or are they asking us to say how big the difference is? This is pretty common in statistics. You won't know whether you should just answer the yes or no question or actually go a little further and say how big the difference actually is. So you might want to just do both. Do the hypothesis test first to see if their difference is significant, and then follow up with a confidence interval to see how big the difference actually is. It's actually very common to do both, because the hypothesis test only tells you if the difference is significant, which, remember, in statistics doesn't mean it's a big deal. It just means it's not necessarily random. And then you can use the confidence interval to say more about like how big of a deal it actually is, whether it's a big difference or a little difference. So it's a good idea to do both of these two things. Okay, moving on, the next question is the same situation, the same study, but this time the variable they look at is the number of unprotected intercourse acts between a subject 4 to 8 months later. It's a number, and so it's a numerical variable. With numerical variables, you don't need to turn it into a percentage. You just take the numbers and average them. And so we can see if there's a difference between the average number of unsafe sex acts, if you will, for the control group and for the treatment group, and see if there's a difference. So again, we're in the situation where we're not sure, do we want to see how big the difference is, or do we want to see just is there a difference? So maybe we should do both. But now, because the data is quantitative data, it makes sense to talk about means, and so we're going to do inference about two different sample means. We can do the t-test for that, and then we can follow up with the t-distribution confidence interval. Okay. Last question. This one was the trickiest. It's a situation where you've got participants who are throwing darts at a target. One in one condition, they use their preferred hand, right? So if you're right-handed, you use your right hand to throw the dart. And then they also use their other hand, and they check their performance on the two different tests. I guess higher numbers are better performance. And so the question is, we want to know whether people really tend to do better with their preferred hand, and if so, by how much. So first of all, the question of whether they do better, that's yes or no. So I guess that'll be a hypothesis test question. And then the follow-up, how much better do they do, that's going to be a confidence interval. So we're going to do both again. Now, which kind of hypothesis test and confidence interval do we want to do? Well, the data here you can clearly see are numbers. They're scores on the, playing darts. So it's quantitative data. It makes sense to talk about the average score when you use your preferred hand versus the average score when you use your non-preferred hand, your left hand for most people. So is there a significant difference between these two groups of numbers? And if so, how big is the difference? Sounds like we're ready to go, except there's one caveat here. Is this one or two samples? It looks like two samples, but it's actually not. This data, each of these pairs of numbers goes with one individual. The first person got 12 points when he used his preferred hand and only 7 points using their non-preferred hand. But these two numbers are not independent numbers from different samples. They're really a single number. I mean, they're really two different numbers from a single individual from only one sample. So what we should do is we should do the matched pairs technique. When you're doing matched pairs, you don't use either of these two numbers, you just use the difference. So if I add to this table here one more column, the difference column, then I can use the differences between the preferred minus the non-preferred numbers to see what those are. So the first person, his difference was 5. Next person, the difference was 7 minus 9. That's a negative number. They did worse with their preferred hand. The third person had 3 points higher, then 3 points higher again, then 1 point. This is the column of data we're actually going to work with. Because the data came in matched pairs, we want to boil it down to one sample's worth of numbers. Then we'll average the difference. And then we'll have like a null hypothesis that says, on average, there should have been no difference. And so the difference should have been 0. And do we have significant evidence that that's not true? And then if so, how big is the difference on average between preferred hand and non-preferred hand? Okay, so here are the two formulas for doing that. The one sample t-test and the one sample t-distribution confidence interval. So watch out for matched pairs data. It only comes up when you have data like this that comes in pairs, numerical data that comes in pairs. You won't have to worry about this when you're working with proportions. Okay. If you have any questions, as always, please let me know. This will be the last new material for the course. Everything from this point out is just going to be review for the final exam. All right, take care, everybody.